Hello, Hornets. In this video, we're going to be taking a look at optimization part 2. So if you haven't seen the first part, I recommend that you do. Let's just take a moment and remind ourselves that optimization is a process by which we are taking derivatives of an explicit function and looking for a maximum or minimum. If we get two values, we will have to make a sign chart and use our first derivative test in an effort to determine what we need to find. In many cases, we will only have one single value that we find, and that will be our solution. So, with the optimization problems, the whole basic issue is that optimization usually gives us an equation that has more than one variable. It requires us to find at least one or more equations to explain a variable in terms of a single variable throughout the entire problem. We call these secondary equations or linking equations. Let's take a look at another example and immediately get ourselves started. A farmer plans to fence a rectangular pasture adjacent to a river. The pasture must contain 245,000 square meters in order to provide enough grass for the herd. No fencing is needed along the river. What dimensions will require the least amount of fencing? And you'll notice that I have a nice diagram here for us to work with. Now, the first thing we have to recognize is that they've told us that we want fencing, and fencing is a perimeter. So I can immediately look at this as x, y, and y, which means that my perimeter is going to end up being 2y plus x. And this is what I want to minimize. Now, if I'm going to minimize it, that means that I have to have one variable, and I have two. So what else do I know? Well, I know that the area, x times y, was 245,000 meters squared. Well, if I'm looking at this, I have two variables I can solve for. I can either find x or y, but because I have a 2y, I'm going to find what x is. This will allow me to do this without multiplying, and therefore it's easier. I'm also going to get rid of my units. Now, because I have only one variable when I substitute, I can now call this the perimeter in terms of y. P of y is 2y plus 245,000 over y. And that's what I want to take my derivative of. Now, we already know in order to take our derivative, we're going to use the general power rule, and we're going to call that y to the negative first. So when we find our y prime, or p prime of y, we have 2 minus 245,000 divided by y squared. I can now do several things. First of all, I can factor out a 2. Second thing I can do is I can get a common denominator, and that common denominator will be y squared. So I'm going to have y squared, 122500, and I factored out the 2 in front. Now this actually factors. We're looking at p prime of y is 2, y plus 350, y minus 350 divided by y squared. Now, in order for us to find our variable, we set our derivative equal to 0. And you'll notice there are two values that will make this work. Just a reminder, we're also using our numerator. The denominator finds us asymptotes, and we already know that's 0. And you'll notice I find y. Y is either negative 350 or positive 350. And because this is a minus, we can get rid of it. It's a dimension. And we know what x is. X happens to be the 245,000 divided by 350. and we get 700. Now I'm going to attach my units, and I would also give my sentence answer that the pasture is enclosed by dimensions of 350 meters by 750 meters in order to have the least amount of fencing used to enclose 245,000 square meters. All right, let's take a look at another situation that we might encounter. Sometimes the linking equations have to come from us. Sometimes it's not just given. There's something there, but we have to actively have some basic knowledge to contribute. For example, a company has started selling a new type of smartphone at a price of $140 minus 10 cents times X, where X is the number of smartphones manufactured per day. The parts for each smartphone cost $80, and the labor and overhead for running the plant cost $5,000 per day. How many smartphones should the company manufacture and sell per day to maximize profit? Now, keep in mind that there are certain formulas that we know. Right? We know, for example, that income is going to be the price times the amount sold. We know our cost based upon what this told us is we have $80 times the number of cell phones made plus 5,000. And since X is the number of cell phones per day, I'm also going to look at this from what the information was given, and that's that I have $140 minus 0.1x, the price, times X. Now, we're trying to figure out our maximum profit. So our maximum profit, P of X, is made by our income in terms of X minus our cost in terms of X. And we have both of these formulas. So we're just going to put that in as 140x minus 0.1x squared, and I'm adding to it 180x. Whoops, forgot that's subtract, Mr. Lamb. Don't also forget to distribute it. So we have minus 80x and minus 5,000. Now this gives us our equation that we're going to work with, and that's minus 0.1x squared plus 60x minus 5,000. Finding my derivative, I end up with negative 0.2x plus 60. We want to find when this is equal to 0, which means I'm going to subtract the 60, divide by negative 2 tenths. Double negative is positive, and I'm looking at 300 smartphones per day. And now I would answer my question by just making a sentence. I hope that helped. Now, be aware that on the AP test, these are the types of questions that they might give you for an FRQ, or at least some part of it. But on the multiple choice, they tend to give you questions of optimization that are more algebraic in nature. Which points on the graph of y equals 4 minus x squared are closest to the point 0, 2? I'm going to quickly draw my picture of this. And you'll notice, here's 0, 2. We know our vertex point is up here. That's 0, 4. And we're trying to find points. Now, if there's one here, I'm going to have one over here. And both of those distances are going to be equal. So I'm going to work with just this single side because it's positive. And what will change is an opposite x value. All right, so here we go. I have my distance formula. The distance formula is the difference between the x's squared plus the difference between the y's squared. Now, when we simplify this, I'm going to get down to x squared in two variables, so I'm going to replace it with the known y value. 4 minus x squared minus 2, the quantity squared. I'm going to keep simplifying this until I get to one single equation. And that one equation has to ultimately have just x's in it. You'll notice this is going to be x squared plus 2 minus x squared, the quantity squared. Now we can start to see where things go. We have an x to the fourth. We're going to be subtracting a 3x squared, and then we have a plus 4. We take our derivative. Now be aware, when I take my derivative and this distance in terms of x, I want to use just the inside. Now I'm going to show you why, but from now on, I don't want you to do this. I want you to take just the derivative of the inside. Because when we take the derivative of this, the power moves in front, the square root drops to the denominator, and the new derivative of the inside piece is up top. Now, when we're trying to find our critical values, we're only using the numerator to find our zeros. Remember, we can find the critical values when the derivative is undefined, but let's keep it simple, please. And you'll notice I now have 0. There's 1. But this also factors. We've seen that. So let's just take a moment and factor this. We have root 2x plus root 3 times root 2x minus root 3. And now I get two more solutions added on to this. Negative root 3 over root 2, which we can call negative root 3 halves, or, and we have this one, which is a positive root 3 over root 2. We'll just call it root 3 halves. Now, I need to figure out what's what. Now, I suspect that it's going to be the two mirrored images. But let's just see how we can use our first derivative test to help us. So I'm putting in each factor one at a time. And my values. Let's just call it 3 halves, 0, negative root 3 halves. Now you'll notice plus, 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 minus, minus, and I'm just going through all of my steps. And you'll notice we get a negative product, positive product, negative product, positive product. These are the two minimum values by the first derivative test. And we now know that at least our x's in the points are the negative root 3 halves and the positive root 3 halves. And we can now find our x, or our y value, excuse me, by plugging it all the way back in. And you'll notice that I'm going to end up getting 4 minus 3 halves in each case. And it comes out to be the mirrored image on both sides of the graph. And our answers are right here. Alrighty. I hope this has helped, Tornets. And please take care. Be well and be safe. And we will talk to you soon. Thank you very much, and good night.